Great, thank you. So welcome to the next session today. So our first talk will be by Antoine Pechetot, who will be telling us about LISA. Please go ahead.
Yes, thank you for letting us presenting LISA. And it was supposed to be Robert Cardwell presenting, but unfortunately he was not able. So I will try to do my best, but the slide are a bit general slide for LISA presentation, and not fully dedicated to the topic of the workshop. Sorry about that. So, oops, can you see my slide? And is the sound okay?
Yes, we can hear you and see your slides and the cursor.
Okay. And can you see the slide changing too?
Yes.
Okay, very good. So I will start presenting the instrument, first the space segment, and then that is the hardware, the spacecraft that will go in space, and then the ground segment. Then I will present the gravitational wave science that we can do with LISA, and then the organization and the status of the mission. So you have seen this graph many times, and so when we are talking about LISA, we are talking about observing gravitational wave from 2 × 10⁻⁵ to 1 Hertz. So in the millihertz band. What is the LISA mission? So the LISA mission is laser interferometer space antenna. We have 3 spacecraft on heliocentric orbits and distant from 2.5 million kilometers. They are following the Earth. From the barycenter is distant from the Earth, so it's 20 degrees, the mean angle, but it goes from, let's say, 10 to 30. The goal is to detect the relative distance change of 10⁻21, so it means few picometers over the 2.5 million kilometers. So in order to be, there are 2 key principles in LISA. The first one is in terms of technology. The first one is we have to be sensitive only to gravity. So in order to do that, the spacecraft protects test mass from external force. So external force are solar wind, micrometeorites, and any kind of thing. And the spacecraft always adjusts itself, like it has been shown. It is shown in this small animation. It always adjusts itself on this test mass using microthruster. And the readout of the test mass position regarding to the spacecraft is done by interferometry on the sensitive axis and capacitive sensing on the other axis. We have 2 test mass in each spacecraft, 1 for each arms. In order to test this idea of keeping the spacecraft on test mass and be sensitive only to gravity almost, we use a demonstrator, LISA Pathfinder. It's a technological demonstrator, and the idea is to reduce 1 LISA arm in 1 spacecraft. The operation of LISA Pathfinder, so the launch was in December 2015, and the operation were from March 2016 to June 2017. And LISA Pathfinder is testing inertial sensor, drag-free and attitude control system, interferometric measurement between 2 free-falling test mass, and microthruster. And you can see here the space. This is the core instrument with the 2 test mass and the optical bench between the 2 test mass. And here you can see the full spacecraft with the microthruster around the spacecraft. The LISA Pathfinder, this is the first result of LISA Pathfinder after 45 days of operation, and it was a real success because we directly exceed, we were directly much better than the requirements, and we kind of directly reach what are the requirements for LISA. It was not the initial goal. So we are sensitive to there are 3 frequency band. We can cut the spectra in 3 frequency band. At high frequency, we are it's the interferometric noise, and we are very good in terms of interferometric noise. We are, I think, 100 times better than expected from the on-ground measurement. But unfortunately, for LISA, it's not the most important part because this will be dominated by other noise, as I will show in the next slide. In this region, we are just limited by the Brownian noise, so the molecule that that hit the test mass. And at low frequency, we are limited by various type of noise, temperature noise, the fact that we have to actuate to keep the two test mass in the same spacecraft due to the autogravitation of the spacecraft, etc. So it's this band is less clear, but well, I would say we understand 50% of the noise in this band. This is the final measurement that we from LISA Pathfinder, and you can see if you compare to the LISA requirement, we are much better than the LISA requirement. So LISA Pathfinder was really a success. Now a second part, a second important point in LISA mission. The interferometric measurement. Or we are measuring this picometer relative fluctuation between over the 2.5 million kilometers. So we have our instrument in space, and inside one spacecraft, we have two tubes here, as you can see in the LISA core assembly, the two MOSA, movable optical subassembly. And in each of these tubes, if we open the tube, we have a telescope, an optical bench, and the test mass behind. So here it's a cut view, so you can see the telescope, the optical bench, and the test mass inside its housing. Here it's a zoom on the detail of the optical bench with a multiple a passive phase and an active phase with the photodiode amplifier in particular. And the idea of the measurement is we are doing multiple measurements. We are measuring the test mass, the position of the test mass regarding to the spacecraft, then the distance between the two spacecraft, and then on the other spacecraft we are doing the other measurement, test mass versus spacecraft, so we can recompose the test mass to test mass measurement. In practical, it's it's much more complicated because we are doing that in what we call virtual interferometry, but the basic idea is this. So we are doing six. We have 6 optical bench, and in each of these optical bench, we are doing what I already said. The distance, the spacecraft. Here it's written optical bench, but it's the same because the optical bench is attached to the spacecraft. Test mass versus optical bench, reference between the two optical bench of the same spacecraft, and then we are doing transmission using the sideband of the laser, and we are also using the laser to measure the absolute distance between the spacecraft. So this is the measurement distance between the two spacecraft. This is the measurement here behind and with this of the test mass spacecraft, and this is the reference measurement. So we are doing heterodyne interferometry with carrier. Using the carrier frequency for the main interference, the interspacecraft measurement. So it's in this signal that we will get Gravitational wave. We are using the sideband to transfer the clock jitter noise because we need to have a reference. We need to kind of synchronize the clock, or at least have the drift between the different clock on each spacecraft, and in order to correct some additional clock jitter. And we are also doing, as I said before, the ranging measurement, so the measurement of the arm length using a pseudo-random noise. In terms of interferometric measurement, we have quadrophotodiode to measure also the phase and the angle of the beam. We have phase meter that are the core, I would say, core unit in the spacecraft in order to provide the measurement. It's a complex phase lock loop system with multiple filters to provide data at a sampling rate of 16 Hertz. We have a number of mechanisms, the point ahead angle mechanism, so because the emission and the reception are not in the same direction. We have the optical assembly tracking mechanism because the triangle is not perfectly equilateral. So we don't have perfectly 60 degrees plus minus 1 degree. So we need a pointing for this tube. And we have other system like beam alignment mechanism and fiber switch unit. The science, we also have science diagnostic in order to have it's the auxiliary channel in order to cross-correlate that with the signal to understand what we have in our data. In order to what did we test? How are we in terms of technology? So with LISA Pathfinder, we have validated all the technological elements that are linked to fly a spacecraft from a test mass and to local interferometry. And what we have to demonstrate, and what is partially demonstrated, is the precision interferometry over 1,000,000 kilometers. So for that, we need a laser frequency stabilization that it has been tested partially with the GRACE follow-on mission. We need to understand the tilt-to-length coupling, the stray light, the high stability of the telescope, in particular regarding the temperature fluctuation, the phase meter and the distribution system, and the constellation acquisition. And all these red thing, we are developing on-ground demonstration and simulation. In terms of noise, the dominating noise are this. We have all this noise, and this particular noise, the laser noise, for example, that is, if we are talking in relative frequency fluctuation, it's 10 to the minus 13 compared to the gravitational wave that we want to detect at 10 to the minus 21. You see clearly that we have to suppress this noise, and we are doing that by the on-ground processing. It's a step called initial noise reduction pipeline. We also, via this process, we are also correcting for the clock noise, for the longitudinal spacecraft jitter, and for the tilt-to-length. Now, let's talk about the LISA data. So we have a large number of sources that we want to detect in the LISA data. I will go back to the source later. So we have all these sources emitting gravitational wave. We have our instrument that is a survey type observatory, and that emit that send to ground phase meter and auxiliary channel, let's say. This is received at ESOC in Darmstadt, and then process for calibration correction, resynchronization of clock, and the process that is called time delay interferometry. The idea of time delay interferometry is it's mainly to reduce the laser frequency noise, and you are in the laser frequency noise appear in at least 2 measurements, each laser frequency noise. And the idea is to combine this measurement in order to suppress this noise. But these measurements are not done at the same time because you have the propagation between spacecraft. So you need to combine delayed measurement. And with this process, you form virtual interferometer by processing. Typically, we can form 3 TDI channels with 2 independent. And then we are doing the data analysis of gravitational wave on this TDI channel, and to extract a catalog of gravitational wave source with their waveform. This is the name of the data level, and this part is under the responsibility of European Space Agency, and this part, the gravitational wave extraction, let's say the extraction of the science, is under the responsibility of the LISA consortium. In terms of what we are doing on ground, with more details now. So as I say, we need to do some noise reduction in the first step of the pipeline. Then we need to extract the gravitational wave and then produce the final product. If we open the box, it's a bit more complicated, and this is just an example. You have several schemes possible for this noise cleaning. And you see that you have all this part that is TDI. You have a part that is clock synchronization and ranging. We are using Kalman filtering for doing that. You have this part that is correcting for some additional noise due to the clock imperfection. You have this part that is correcting for misalignment between the various optics and the various elements that we have in our instrument. Now, in terms of gravitational wave extraction, we have two main categories of pipeline. The one that we call low latency, it's for extracting alerts. So this one has to run very quickly, and the purpose is to do two things: detect new source in the new segment that are coming, and refine the parameter estimation, and in particular the sky localization of the existing one, as for example the supermassive black hole. So if you have a supermassive black hole merger during the observation, or let's say during the pass when we are communicating with the spacecraft, you improve over the last few hours the sky position by a factor, let's say between 2 and 10. So you want to have this information and to provide this information to other instruments in order to maximize the possibility of having counterparts. So this pipeline is quite important. And the other one that we call deep analysis is really for extracting as much source as possible, taking the time to extract all of them. And for all this, we have multiple pipelines running in parallel. So, okay, I already talked about that. It's another version of the initial noise reduction pipeline with this main element that is TDI. And you can see that there are several steps in this. We also do some instrument monitoring. In terms of extracting the gravitational wave source, the complexity is in the large number of sources and the fact that we have data that are not clean. They will be real data with gap, glitches, non-stationarity of the noise, and maybe some uncertainty on the noise level, which is particularly important if we want to detect and characterize some stochastic gravitational wave background. In order to develop and be ready to that and to see what we can do really with the instrument, we have a working group that we call the LISA Data Challenge Working Group. And the goal of this is to organize the development of the data analysis for LISA. We generate data set, and they are provided to the community. Everybody can participate to that. We organize the development of some of the data analysis method within the consortium, but it's not only the consortium, it's really open to any participant. And then we are increasing, and we analyze the result of the various participants and try to compare and to see if there are challenges that are particularly hard, and to see where we have to put some effort. We are increasing the complexity of the data set. This is both on the number of the increase of the let's say the number of artifacts that we are putting in the data. So we want to get closer and closer to what will be the real data. And also in terms of number of sources, we are not directly starting with all the sources in the data set. We are starting we are doing step by step. Here it's a data set where you have so it's the one that we are currently working on. So there is the Gaussian is standard. There is no gap, no glitch. The noise is Gaussian, but we have for example, the full galaxy with all the galactic binary. Plus, on top of that, several supermassive black hole binary that you can see in all the small graph around the main graph. And this data set is called the Sangria data set. I will now talk more about the science, but first, the transition from instrument to science is, as for the other instrument, is what we call the sensitivity. So how we compute, what are the main driver for the sensitivity? So this is this top left graph show the noise, the power spectral density of the noise in the TDI output. That is the input for, as I said before, it's the input for gravitational wave extraction. And there are two main domains. At low frequency, what is represented by this green bar, we are limited by the performance of the drag-free and attitude control system. So it's by the fact that by the acceleration noise, the fact that we are not perfectly sensitive only to gravity, we have other perturbation. So it's really what LISA Pathfinder has tested. And at high frequency, we are limited by the interferometric noise. Then we need, in order to produce a sensitivity curve, we need also to take into account the response of the instrument. And the response of the instrument is not flat, is frequency dependent. And here you see what is the transfer function of the instrument to the greatest wave signal. You see that all this oscillation, this zero that you see, they are due to the time delay interferometry technique that create and there are multiple of the frequency of the arm lengths corresponding. The frequency corresponding to the distance between two spacecraft. If we combine the two, we obtain the sensitivity curve, and it's the curve that you are used to see, I guess. And then now let's look at all the sources and see what we can detect and what we can not detect. Let's start with the small one. So the compact solar mass binaries. We have a large number of stars in binary system in the galaxy. The evolution they are evolving in white dwarf or neutron star, and we have the existence of white dwarf, neutron star, white dwarf, neutron star binaries. The estimation is we have something like between 30 and 60 million of sources of such kind in the galaxy. And the greatest wave emission, for most part of their life, they are emitting during the slow in spiral regime as quasi-monochromatic sources, and they are emitting in the LISA band at the millihertz. And for few are coalescing, the neutron star, and it's the gravitational event that are observed by the Ground Bears Observatory. For LISA, we have now something like 10 to 60 sources that are guaranteed source. So we know we observe via electromagnetic observation this source, and we know that they are emitting gravitational wave at the in the millihertz band, and they have to be seen by LISA. It's a way of checking that everything is working fine, and maybe to calibrate the instrument. We are currently investigating this possibility. If we can really calibrate the instrument, in particular the amplitude response and the phase response of the instrument. So for LISA, we have quite a number of quasi monochromatic sources. They are present during all the duration of the mission. The signal to noise ratio is between 7 and 1,000. And for the source that we are not detecting, there is a confusion noise. That will be a foreground for the other source, because we are only detecting about 20 to 30,000 of source over the 30-60 million sources, and we have something like 10 guaranteed. But now with Gaia, we will be more at 100 guaranteed sources. And in the graph, it's represented by this blue dot here. So this is simulated the 25,000 sources we are detecting. The black dot are the verification binary, and the gray area here is the foreground from all the sources that we are not detecting. Let's increase a bit in mass. So the binaries from two black holes of stellar mass black hole, so between a few solar masses and 100 solar masses. So the one that have been observed by the Ground Base Observatory. So we will observe them in the milliards band with LISA when they are far from merger. They are just spiraling. And of course, this source will also merge in the Ground Base Observatory band. So we hope that we can do multi-observatory observation with this source. And it takes for them a few years to go from the LISA band for some of them, from the LISA band to the Ground Base Observatory band. Yeah, so they are at high frequency they are in the high frequency part of the LISA sensitivity. It's the dot. I don't know if you can see the dot, and this line is really the one that are going to be seen by the Ground Base Observatory. Now the supermassive black hole binaries. So we know that supermassive black hole exists. We have Sagittarius A star. We have the one observed by Event Horizon Telescope. We estimate that there are supermassive black hole in the center of a very large number of galaxies. And since the galaxies are merging, we are expecting we should have some supermassive black hole binaries. Michael already, it's sources that are not only for LISA, but also for PTA, as Michael already presented before. For LISA, we are talking about sources that are around 10 to the 6 solar masses, while for PTA, it's more 10 to the 8 solar masses. For LISA, we will observe this source in all their regimes. So from the in-spiral part described by post-Newtonian, the merger, and the ring down. And the duration can be for few hours for the very massive system to several months. The duration of the observation, so the time the source spent in the band. The signal to noise ratio can go until few thousand, and we are expecting to have something between 10 to 100 of this event per year. And it's really one of the key sources for LISA. In particular, we are hoping to do some multi-messenger, multi-messenger astronomy with this kind of source. In this plot, you can see that here is the mass on the x-axis and the redshift, and basically it shows that if you have a supermassive black hole binary between 10 to the 4 and 10 to the 7 solar masses merging in the universe, they will be observed by LISA. If they are not very badly oriented regarding to the detector. But in most of the cases, it's not like that. And on the sensitivity plot, it's this track going, this big track that you see in the middle. I will speed up a bit because of the time. So okay, I already. Now let's mix a big one with a small one. It's what we call the extreme mass ratio in spiral. So the mass ratio for this source is 1,000. I wrote 200, but 200 is more for IMRI, intermediate mass ratio in spiral. So it's more 1,000 for this kind of source. And it's a very interesting source because they can give information about the geometry around the black hole. We can test GR in a strong field regime, and the emission is between 0.1 millihertz and typically the 100 millihertz. About the event rate, we don't know. It can be 1 source per year. It can be 1,000 sources per year. So it's yes, I already said that, and the signal to noise ratio can be from tens to a few hundred. The waveform is very complex, and the extraction of this source is quite challenging. So this is the harmonic in the sensitivity plot corresponding to one of the sources. And with the MRIs and the supermassive black hole binaries, we can also do some cosmology using the standard sirens logic, so measuring the luminosity distance with the gravitational wave. And if we have a counterpart, we can measure the redshift, and then we can constrain the geometry of the universe. Put some constraint on that.
5 minutes.
Okay. So about cosmological background, I would say it's the topic of the workshop. So we have a large potential for LISA, going from I just list here 2 types of source. I guess you had plenty of talk about the various possibility in the previous day. The first here is the first order phase transition in the very early universe. This can produce this kind of background in the LISA band that will be clearly detectable if there is a if, you will see after. And this is the same thing, but with another stochastic gravitational wave background, but from cosmic string. This is from the review of Chiara and Danny from 2018. Why there is an if? There is because the detectability and the characterization of this source is quite challenging. First, we need to separate this stochastic gravitational wave background from the instrument noises. So it means that we need a certain knowledge on the instrument noise. We are currently studying the possibility of calibration of the instrument in order to understand this noise. We also need to explore as much as we can the use of the various interferometric combination that we can do with the time delay interferometry process. We also need to separate this source from the foreground, from other sources like the galactic binary foreground and the more important, the one formed by the stellar mass black hole binaries. And we need to also explore the data analysis possibility. So this is some preliminary work that has been done by Nikos Karnezis. There are similar work that have been done by Raphaël Furgier et al. But we are starting, and we need to work more on this side. So this is the sensitivity with all the sources together. Now, to finish the talk, I will give a quick, so this is, the sense objective of the mission. And you see that the SO7 is clearly the stochastic gravitational wave background to understand the early universe and the TAVE scale particle physics. And all the rest is the compact binary, black hole, MRIs, but also the fundamental nature of gravity, in particular testing GR, and this is the standard SRN in SO6. So about the status of LISA mission, so we had after success of LISA Pathfinder and the detection of gravitational wave from ground, we had a call for LISA mission, the submission of the proposal in 2017. Then it has been accepted quite quickly. In June 2016, we had a phase 0 during 2017 and 2018. Then we are in phase A, and we are finishing the phase A. The phase A, we are studying on the consortium side the payload, plus you have 2 competitive primes working on the platform and partially on the payload. Then we will have the phase B1. A big step will be the adoption. After the adoption, it's the point where all the agencies say exactly what they will do, what they will provide, and we really start the construction. Here we are still in a very advanced design phase, and then the launch is expected for 2034 because it takes 10 years to construct these 3 spacecraft with 2 MOSA. One of the challenges is how to construct all this piece of instrument, because we have to construct multiple of them. Then we have 1.5 years to go to the location. It's 9 months of commissioning. Then 4 to 6 years of nominal mission, plus a possible extension to 10 years. So here's the same timeline. And what are we doing now in phase A? It's a first definition. In fact, it's quite advanced. The organization, the performance, and for the ground segment, we already started because it's challenging. We already started to be very active. The organization of LISA, so it's an ESA lead project. You have two primes, Airbus and Thales, working on that. The NASA is a junior partner, providing the telescope, the charge management system, and the laser system. And then you have the consortium of all the member states plus US here, providing also a part of the ground segment. All the green box, DDPC, it's Distributed Data Processing Center. It's the ground segment that will extract the gravitational wave. Then you have other consortium provided items that are the interferometric detection system, all the blue box, one of the kind of blue box. You have the diagnostic from Spain, and you have also from France all the ground segment equipment that will test the instrument. In terms of the number of people involved in LISA, we have a LISA consortium with 1,400, now we are almost 500 persons. You have full member and associates, so the full member are people that are already committing the time in LISA. I will skip that. This is the organization of the consortium. You have the slide if you want to see them, but we have the formulation management team is for the project, and this is for the science study linked to the mission with the working group, and the working group are very active. We have 500 for the astrophysics, 300 for the cosmology. Regular workshop in this working group. They are producing white paper that describe the state of the art of the LISA science and multiple projects within this working group. And I will stop here with my conclusion. And I think LISA has a huge potential for a lot of things, and in particular for stochastic gravitational wave background, even if it's a challenging type of source. Thank you.
Great, thank you very much for that talk. Are there any questions? If so, please raise your hand and unmute yourself, and you can go ahead and ask them. Yeah, please, Salvatore, go ahead.
Yeah, thanks, Antoine. I have a couple of questions. One is on the mock data challenge, something which has been discussed over the last couple of days at the workshop. It's memory. So I was wondering whether you already have or you plan for the CBCs for which you do see measuring down to also inject signals with memory.
It's not. We can do that. We did not really talk about that, but it's completely feasible. So if people are interested to study this kind of effect and to see the ability of the mission to do that, we can do that. It's not exactly in the current plan, but it's not a big effort to put an additional challenge for some of the source or to include that in the normal challenge. But at the moment, it's not yet included. But it's a very good point. Yes, we can do that.
Okay, thanks. And another question, although I realize it may be too early, like a few years early, I was wondering whether in the consortium you have already started discussing what kind of data policy you will have, respective to data being available after which delay.
It's not too early. In fact, because we have. If you see the timeline that I was showing with the adoption in 2024, for the adoption, ESA wants a first data policy to be drafted and to be agreed. So it means that within the three next year, we have to define the data policy, and it's an active, and there are a lot of discussion, as you can imagine, on this kind of topic. And I'm leading the working group in the LISA board discussing about that, and we are taking a lot of input, in particular from the ground-based observatory community, because it was also a challenging thing for them.
All right, thank you.
Are there any other questions? If not, thank you again for that talk. And I guess we should move to our next speaker.
Thank you.
Right, so next up we have Salvatore Vitale, who'll be telling us about Cosmic Explorer. So if you can go ahead and share your slides. Okay, I can see your slides.
Yeah, you can see them and see the mouse and everything, right?
I don't see the mouse at the moment. Just try moving it around. Yeah, I can see it now.
What
and
about
I can
now?
hear you as well. Yes, that works.
All right, fantastic.
So please go ahead. Thank you.
Thank you. Let me start the timer so I don't go over time. All right. So first of all, let me thank the organizer for inviting me to talk about Cosmic Explorer and what they can do for you in a few years. All right. So let me start by saying that I'm also talking on behalf of a few other people referred to as the Cosmic Explorer project team. I will say what these are in a second. And also for those of you who are on social media, Cosmic Explorer has a Twitter handle that you can follow if you're so inclined. All right, so let me start with a very quick 1 or 2 slide summary of where we are, where we means gravitational wave astronomy from the ground, specifically with interferometry. Right, so as you all know, LIGO and Virgo have been collecting data since 2015. So for the last 5 years, we have had 3 observing runs, the last of which has lasted for roughly 1 year. And during that time, we have made, during the last science run, we have made public 56 gravitational wave candidates, which is 1 per week, which is pretty amazing if you think that 6 years ago, we had never seen a gravitational wave. And as of very recently, as of a couple of weeks ago, we have made public the discovery of the first and second neutron star black hole merger ever seen by humanity, which is pretty nice. We have had a few oddballs, like incredibly heavy black holes, bordering the intermediate mass black hole range, very light black holes, and so on and so forth. And you can find here a list of the recent collaboration papers. All right. The one thing I also want to stress from the plot on the left, it's how incredibly quickly the slope of detection versus time has changed between O2 and O3 with implementation of quantum squeezing. And so as the detectors improve in their sensitivity, we'll expect this slope to get even a bit steeper and detect really 1 binary black hole or a few binary black hole every week. So that's all great, and yes, as you all know, allowed us to already start tackling open questions in astrophysics, physics, and cosmology, right? But my job today is to look at the at the other side of the coin and stress that while we all love the current detectors, they are intrinsically limited by their size and geometry, right? So you can do the math, and what you discover is that even once at design sensitivity, current detector will be limited to, first of all, observe objects in the local universe, where local means, for me in this case, redshift of 1-ish. And the number will be great, thinking that we are really starting this, but they will still be on the hundreds probably per year, and most of them will be binary black holes. So if you compare this with the LISA numbers, of course, we're order of magnitude below. The signal to noise ratio will be, still low to moderate. We will see some events with a scenario of 100 or so, or a few hundreds, but most of them will still be lower than that. And we will see more and more events with a counterpart on the electromagnetic spectrum, but they will still be probably not, hundreds or thousands, right? You can do the math. We have been now in this business for 5 years, and we have seen only 1 event with a counterpart. Here there is a nice plot from the latest LBC population paper that shows a reconstruction of the merger rate for binary black hole as a function of Z, to show that it's right now consistent with the star formation rate pretty much within error bars. The point I want to make though from this plot is to show you how the error bars are quite large, basically an order of magnitude at 0.1. And the reason is, as I said earlier, that even when we are design, most of the events we'll detect will be in this redshift range. And so it will be harder or impossible to see resolved sources at redshift higher than that. So to go past this limitation, we really need to build something new, right? And we typically refer to these new objects as third generation detectors. And with these detectors online, we are talking of more or less facilities which will have a strain sensitivity of a factor of 10 better than advanced detectors. And with those, you'll be able, as I show in a second, to detect binary black hole pretty much everywhere in the universe. We will have a lot of events with high signal to noise ratios on the thousands, and the number of events will go from a few hundreds per year to hundreds of thousands per year. And I'll talk about the timeline, but we target operation for the second half of 2030s. Now, there are several concepts around, a couple of concepts around the third generation detector. The one that probably many people at the workshop are familiar with, based on the last few days of conference, is the Einstein's telescope. So what this is a triangular shaped detector with 10 kilometers arms. It's planned to be underground such that it can access, you can have good sensitivity, in the 1 to 5 Hertz region, so a very low frequency compared to LIGO and Virgo. It's a rather mature design. It has been around as an idea from, for more than 10 years, and the first design report was published 10 years ago, right? And a very, very good news for the field is that just a couple of weeks ago, the Einstein telescope was included in the European Strategic Forum for Research Infrastructure roadmap, which means that its probability of happening in the time scale that we hope are actually, even higher now. All right, so as I said, many of you know about the Einstein telescope. My job today is to introduce you to the Cosmic Explorer, which is an American design for next generation detector. So there are quite a few differences in terms of design. The main one is that we are not thinking in the US about a triangle because space is not a problem in the US. So we are thinking of keeping the current L-shaped geometry, like current detector, just make it bigger and go from 4 to 40 kilometers arms. And it is a possible depiction of how this will look like. You also see behind me. So it'll be on the ground, and it can be optimized. I can say something about this later if people are interested, to target either high frequency of science goals on the kilohertz region or medium frequencies, so in the hundreds of hertz region, by changing some mirrors. All right. The one thing I want to stress is that we really don't have to think about this as an competition between various designs and detectors, because as we all know in this business, you really want to have a network to do the best possible science. And this is true enough that the Gravitational Wave International Committee, which is also called GWIC, has put together a committee to look at next generation detectors and the science you can do with them. And I want to advertise this URL, which basically entirely focuses on 3G science from the ground and does dozens of useful documents and links you can follow. Here you see a screenshot of actual white papers on the science, the R&D needed, the computing, and so on and so forth. There are quite a lot of them, so it's a great resource to have. Now, back to Cosmic Explorer, though, what I want to say is that the NSF, realizing that we have to get the ball rolling to, if we really want to have something in the 2030s, has founded 3 years ago a team of people to which I belong, to work and write on an horizon study to explore design options and scientific potential of ground-based next generation detectors in the US specifically. We have recently released a rather mature draft that you can read here in this URL. My slides are available on the conference webpage, so you can see this later if you cannot write them down. Here is a screenshot of the cover page. So I really invite you, if ground-based detectors can be useful for your science, to have a look at that and at this and send us comments if you want. It's a rather long document. It has 100+ pages and covers everything from science to research and development needed to make detectors happen, to engagement with the community, since these detectors will probably have to be built in indigenous land, to policy and so on and so forth. So it's really a great resource to have. In terms of timeline, I mentioned mid-2030s as a target. And as you know, if you have done this kind of things, there is a lot of wiggle room. But that's our best guess today. If things goes as we hope. We are in 2021, so we are at the end of producing this Horizon study, after which there are still a few years and steps required with the NSF and other entities to have construction hopefully starting just before the 2030s, and hopefully go online in the mid 2030s. Again, there is a lot of wiggle room here, and I don't want to go in detail since these things may change. But in the Horizon study, you will find some more details that I can give you in 20 minutes. And the idea is to operate this pretty much as we do today, with a sequence of commissioning periods and observation periods to improve the hardware as you go along. All right. So the remaining of my talk will really focus on the science that we can do. So in the Horizon study, we identified a few key science goals that we can reach with this kind of facility. This won't be an exhaustive list in my talk today, but the three main themes that we have identified are called the black hole and neutron stars throughout cosmic time, which is really the topic I'm going to spend most of my time talking about today. And then dynamic of dense matter and extreme environments. So this is stuff like equation of state of neutron star, post-merger oscillation, quark matter neutron star phase transitions, and so on and so forth. And then finally, something called extreme gravity and fundamental physics, which is rather self-explanatory. All right. How do we do that? Well, we do that with incredibly sensitive detectors. So let me show the kind of mandatory slide with the sensitivity. In here, you have on the x-axis the frequency, and on the y-axis the noise. So lower, it's better vertically. And you see here a Advanced LIGO curve as of the third science run tree, and a projection for LIGO Plus, which it's a sensitivity we could reach maybe in 2025, and Voyager, which is a planned cryogenic upgrade of the LIGO detectors in the same facility that we have today. And then at the bottom here, you see the two 3G detectors I mentioned, Einstein Telescope and the Cosmic Explorer, right? The main difference that you can see is that because Cosmic Explorer, it's on the ground, it will not reach the exquisite low frequency sensitivity of Einstein Telescope in the Hertz region. Our sensitivity degrades there, but we will have, because of the longer arm length, a better sensitivity in the bucket, so in the region between, say, 10 and 100 Hertz. The one thing I want to stress is that as I've listened to the talks in the last many days at this workshop, I've seen many people having and using for their work the Einstein Telescope curve, but not the Cosmic Explorer one, and which is understandable because we are more recent. But I want to advertise that if you do want to use Cosmic Explorer curves for your publications and work, you can find all of these curves pretty much publicly available. Here there is a link that you can go to and download. These are just ASCII files, I think, or something like that. All right, so this is great. You can also convert the sensitivity into horizon plots and ask yourself, how far can these detectors, existing or planned detectors, see compact binaries of a specific total mass, right? That's the nature of this plot. On the x-axis, you see the total source frame mass in solar masses. On the y-axis, you see the redshift, and the lines give for various detectors given in the legend how far you can see them if they are optimally oriented. And then you see three lines that mark remarkable events that we have seen so far. So that would be a neutron star binary here, at around 2-point-something solar masses, a 30 solar mass black hole, like 5914, and a 150 solar mass black hole, like 190521, right? So the point here is that, as I mentioned earlier, while with Advanced LIGO, you may see objects up to 0.1, maybe a bit more than 1 if they're really massive, most of the high redshift, even higher redshift universe, it's entirely precluded to you. And things will get a bit better with Voyager, but it's really when you go to 3G that you can see that you can say that you will be able to access black hole binary pretty much as far as there are stars in the universe, and even farther away than that, right? So the way to Z of 10 and above for binary black holes, and the redshift of 2 or 3 for binary neutron stars, which is pretty amazing. Right, and the reason why people like me love this kind of plot can be, or this kind of science can be better probably represented with a different plot, which shows where where you expect black hole binaries to be as a function of the redshift on the x-axis, right? So here I have, again, on the x-axis redshift. On the y-axis, I have merger rate in units, so mergers per gigaparsec cube per year, and the orange and blue line gives us, through population synthesis analysis, the expected merger rate as a function of Z from binaries in galactic field and in globular clusters. And you can see that they pick a redshift of 2-ish. And then you see also a black line, which is the total contribution, summing all the population. The green line here gives, again, based on population synthesis code, the expected merger rate of black hole remnant from population 3 stars, which of course we have never seen yet, either in the M or in the gravitational wave sector. So it will be a great interest to be able to access population 3 remnants. And the point this plot is making is that Advanced LIGO and Virgo and Kagra will only be able to see black holes up to this peak here. Even Voyagers, even cryogenic updates will entirely miss the peak of population 3 stars, while Cosmic Explorer and Einstein Telescope will have sensitivity which is much, much larger. So what you can do, and again, I want to stress, you want a network for this kind of science, not a single detector, is to access this extremely high redshift population. And you can do things like this. Here I'm showing from a paper that we'll refer to in a second, an unmodeled reconstruction in gray based on Gaussian process regression using, this is probably of the order of 4 or 6 months of 3G data. And so what I want to show you is that if there is a population 3 black hole merger, you can, with a few months of data, pretty much pinpoint its merger rate evolution with 3G detectors. And similarly, if such population does not exist, you can exclude that it's there, because you get it, you basically measure the tail of the astrophysical population getting down. You can do more. You can try to use, again, in an unmodeled way, this data and measure the redshift at which population 3 binary black hole peak. And this is shown in this plot. It's very complicated. I won't go through it in detail. I just want to say that it can be done. So here the square is the true value of the peak, which is a Z of 11-ish. And the GPR is the Gaussian process regression measurement of that value as you vary the mixture fraction between the globular cluster and the galactic field. It's a bit complicated, but the point is that it can be done with little or no model. Even better, in the last 2 minutes, we can go after primordial black hole mergers, which was another hot topic in the workshop. Those will merge at even high redshift, probably. Here you see a potential merger rate distribution from various papers by De Luca and Rydell as a red curve. And as we have discussed, I think yesterday or a few days before, you can theoretically use mass and spin distribution or eccentricity distribution as tracer of the nature of the primordial nature of the black hole. But an even safer way, it's use the redshift, right? Because if you see black holes at Z of 30 or 40, it's very unlikely that they come from astrophysical channels. So what we are currently doing with various people, this work led by my student Ken, who is on the audience actually, it's again show how you can use a Gaussian process method. So this is an entirely model approach, and show here how, whether you do or you don't have mergers from PBHs, which are shown here as this orange curve, you can, this plot is with 7 months of 3G detectors, pinpoint pretty much the merger rate all the way to Z of 40, which is pretty amazing if you think about it. All right, I have only 1 or 2 slides left, and I'm basically good with time. The other thing I want to mention, again, because this was a hot topic during the conference, is stochastic background. Of course, if you add to an Einstein telescope 1 or more cosmic explorer, you can increase the sensitivity to stochastic background searches. So here you see a plot of frequency and the omega stochastic, defined in the usual way. And here there are various curves. I won't go through all of them in detail. These are various combinations of Einstein telescope curve D and the Cosmic Explorer, either of 20 or 40 kilometers. And as dashed lines, you see a few possible stochastic background from inflation, so roll inflation, cosmic string, or preheating, right? The point I want to make, more than going into details and say what can or can be done, is that you can also download these curves and use them for your analysis if you want. Everything that you see in this plot should be available in this public document. All right, the very last thing is that I mentioned 40 kilometers and then 20 kilometers. Why? Well, because we are still thinking, and the community is still thinking about what is the best and optimal composition of a 3G network and what's the best trade-off between money and science, right? So some of the questions you may want to approach is 40 kilometers really necessary, or is 20 enough? How many of them do you need? Can a previous generation detector help? And so on and so forth. So if you are interested in this kind of questions, you can look again at the Cosmic Explorer Horizon study, where there is a whole section of a trade study that tries to, again, quantify what kind of science you can do as a function of your network. And you can contribute to all of this. That's my very last slide, because there is a lot of science that can be done, and there's a lot of important decisions that can be done and have to be taken now. Of course, I can cover everything in 20 minutes. So the message, I guess, is get involved. There is numerous opportunities to play a role in C. You can join our consortium following this URL. We are having monthly calls, which are open to everyone in the consortium, both on the science case, and here there are contact links if you want, and on, if you work on the instrument, on the research and development needed to make this detector happen in 2030 something. Thank you.
Great, thank you very much for that talk. Are there any questions? Let's see at the moment.
While people think, I can use some of my question time allocated to say some of the other things that can be done with which are probably relevant for this audience. One of them, it's searching for ultralight bosons, or like axion clouds. A few speakers have mentioned the possibility of looking monochromatic signals from axion clouds. Another thing that you can do is exploit the fact that axion clouds will spin down black holes, right? So if axions exist of the right mass, the spins of the black hole you detect in binaries should preferentially be small, right? And we have already, I'm advertising some work on my student, start doing this with Advanced LIGO and Virgo. But again, you're going to have hundreds of events. With Cosmic Explorer and ET, you will have hundreds of thousands of events. So for those of you who know this business, it means that you can do that with exquisite accuracy. The signal to noise ratio will be huge. So this is, for example, measurements of spin, mass ratio, and distance for an event like 150914, but now detected by a Cosmic Explorer facility and an Einstein telescope, where the SNR will be of the order of 2000. And you can see how incredibly small these uncertainties are. And so if you are after things like test of GR, where you do really care about exquisitely small error bars, that's also where you can win. All right, I'll use also the question time. So
Sure, I think we have a question. Just unmute yourself and go ahead, please.
Hi, Salvatore. You mentioned in one of your slides that that the instrument can be optimized to either look for high frequency that is in the kilohertz sources or in the hundreds of hertz. So that's quite a wide range that to be able to optimize over. So can you maybe describe what that actual process involves and how that's possible?
Yes, I can say something. Not being an instrument person, my answer will be disappointing, and being very conscious also of the fact that we have in the audience people who actually know what I'm talking about, for real. Anyhow, so the idea here is to play with something called the signal recycling. So you change the way some of the mirrors in the detectors operates, right? And by doing that, you can, of course, you have to decide, right? You have to lose somewhere. You can either improve your sensitivity in the high frequency. Of course, that comes at the cost of making things a bit worse in the bucket. So this is shown in these plots here, which are really the same thing. The right one is a zoom of the left one in the kilohertz region. So what is shown here is, again, the strength plot of frequency versus noise. These are various Cosmic Explorer length from 10 to 40 kilometers, because again, as I CB stands for compact binary optimize. So this is a configuration where you use the recycling of the instrument in a way to improve that the sensitivity is best in the hundreds of hertz region. And the dashed line, which is PM, stands for post-merger optimize, where you do things best pretty much here in the 1.5 to 4 kilohertz region, right? And now I cannot give you the instrumental details of how this happens in practice. The thing I know, which is relevant for me as someone who does that analysis and want these instruments to work as long as possible, is that this is an operation that does not take, it's not a decision you make once and you're stuck with it. This is something that you can do in between science run. As I said, we have science run and then commissioning for like 6 months or 1 year. During this 6 months to 1 year, you can modify these mirrors such that the next science run works on the other optimization mode, right? And now, of course, the reason why we care about potentially 1.5 to 4 kilohertz is, as the name suggests, is for post-merger physics. As many of you will know, after the newly born neutron star is formed, there are these post-merger peaks, which in the frequency domain, depending on the equation of state, will be somewhere in this mass region. And the problem, especially if you build very long detectors, is that you will have very poor sensitivity in there. So that's when first the idea of using this tuning to get better sensitivity in this region came about. Right. So really, the way we are approaching this, it's a dynamical process. Like you may run for 1 year using the compact binary optimization, where you have a great sensitivity here. That means you're going to get hundreds of thousands of CBC, of compact binaries, and then you may decide that you have learned enough for a while, so you can do this next science run running in this way and focus on neutron star binaries, for example. I hope that answer at least part of the question. I'm sorry I cannot go into the details of the instrument. It's just not my job.
No, thank you very much.
Great, thank you. Thanks for the talk. So I think we should probably move to our next speaker. So our next talk will be by Rafael Flaja, who will be telling us about primordial gravitational waves at CMBS4. Yeah, I can see your slides. They're now full screen, and I can see your cursor as well. So please, whenever you're ready, go ahead.
Okay, thanks. Well, first, thanks for organizing this nice meeting, and then thanks for asking me or asking CMBS4 to present what our current status is. And so before I talk about S4, I want to briefly take a step back and say what the status of CMB observations is more generally, what the community is doing right now, what the plan is for going forward, and then we'll see how CMBS4 fits in and what you can expect for the detection for CMBS4. I won't spend much time on the first part because I think everyone here knows what the Planck satellite is, roughly what the results were. So here is I'm just showing you one of the nice component separated maps and some of the beautiful angular power spectra. Here is the temperature power spectrum. Here's the polarization, E-mode polarization power spectrum. And you see that the theory and data really agree extremely well. And this has tightly constrained any departures from the simple lambda CDM model and established that the early universe is really remarkably simple in the sense that it's just described very well by a few parameters. In the meantime, on the ground, there's a lot of activity still with experiments at the South Pole. So there's SPT, there's the BICEP Keck series of experiments. SPIDA recently released the results from their first flight. There's Polar Bear and Simon's Array in the Atacama Desert. There's Advanced ACT, which also recently had a number of results. There's CLASS. So there's a number of experiments going on. And given that we have these nice measurements from Planck, I want to briefly explain what the goal is going forward, what these experiments are looking for, and what we're looking for going forward. And to me, one of the easiest ways to illustrate that is by just showing you a plot of all the angular power spectra in one figure. So this is the temperature angular power spectrum that you saw before. This is the E-mode power spectrum that I also showed you just now, shown in the same plot. You see that the level is significantly lower just because it's not 100% polarized. And then, of course, there are the lensing B modes and potentially the gravitational wave signal that we're looking for. And so what you see in this figure is that what Planck has done is had essentially extracted all the information that is there in the temperature. It's not completely true, but it's close to true, because if you look here, you see that the CMB signal, which is the light gray line, is dropping exponentially because of silk damping, and extragalactic foregrounds are starting to take over. So even if you measure at higher sensitivity and higher resolution, you're not gaining a lot more information about the primary CMB. So in that sense, temperature is essentially done. But if you look at polarization, you see that here there's the nice measurement by Planck. But you see that here, if you go to the smaller scales, eventually the Planck sensitivity isn't good enough. So you can extract more data points, but the noise goes way up, so there's no information anymore. And you see that going forward, this is clearly one of the targets. And it looks small in this plot because it's a log plot, but you should keep in mind from your quantum mechanics class that at multiple L, you have 2L plus 1 modes. So there are, in fact, and you should also remember that you can take cross spectra between temperature and polarization. So in fact, there's still more information to be removed, to be extracted from the cosmic microwave background by a significant amount than we have extracted so far. So there's still a lot of information on small scales. And then if you look at the large scales, Planck has measured the large scale E modes, but this was very difficult because of systematic effects like the analog to digital converter nonlinearities. And I think eventually this will have to be remeasured just for everyone to agree and be confident what the measurement here is. And then you also see that the lensing B mode, so caused by a gravitational lensing by structure along the line of sight of the E modes, is starting to be detected by various experiments. But of course, there's also still a lot more that can be learned by making these measurements. And then there's the hope that we will see some imprint of primordial gravitational waves on the cosmic microwave background. Here, this is about as large as the signal could possibly be. Here, this is the kind of signal that would be challenging with the currently planned instruments that would take really yet another step forward. But in any case, you can see that there's still invaluable information about astro and particle physics that can be extracted from the cosmic microwave background. And in what I'm showing you here, you should keep in mind that I'm only focusing on the primary CMB and isotropies, but a lot of the work will actually go into looking for secondaries through the kinetic and thermal Sunyaev-Seldovich effect, which can be used to cross-correlate with large-scale structure, with X-ray missions. And so there's even more information that can be extracted if one also includes the discussion of the secondaries. And in addition, for CMB-S4, we will observe the sky at very high cadence, unlike current CMB experiments, which means you can look for transients in the microwave sky, which will be new and also interesting. Here, I'll focus on the primary anisotropies, and I'll just say a little bit more about the small scale polarization. this constrains, as you probably know, the things like the number of relativistic species through the amount of silk damping and through the phase of the acoustic oscillations, constrains the sum of the neutrino masses through the amount of lensing, constrains dark matter properties, by which I mean maybe dark matter self-interactions, dark matter baryon scattering, dark energy properties. And of course, you can also constrain the statistical properties of the primordial density perturbations by going further out into the to small scales, meaning you can constrain running, you can constrain non-Gaussianity. You can also learn more about the Hubble parameter. Of course, this is always in the context of a model for the CMB. It doesn't really provide an independent measurement of the Hubble parameter directly, but it's still relevant also for the because it constrains any of the proposed solutions to the Hubble tension. The degree scale polarization is the one that we're interested mostly here for this talk, because it's sensitive to primordial gravitational waves, which, as everyone knows, are a pristine relic of the early universe. They hardly are modified at all. And for the simplest models of inflation, the imprint of the gravitational waves on the CMB polarization is essentially the only way to detect them in the near future. Of course, we saw the nice talk in the morning about the SIGO, but it seems that the stage that could detect something is still quite some ways out. It's also worth keeping in mind that these gravitational waves are really statistically completely independent from the density perturbations that we've observed so far, and this provides us a completely new window on the early universe. So that's why that's exciting. And I should have said I put the design here for the telescope because you're going to small scales. You need a big mirror for the small scale polarization, whereas for the degree scale polarization, the measurements will be done with a small aperture telescopes, and I'll motivate why there's the two designs on the next slide. So I don't have time to describe it in too much detail, but if there's questions, I can say more about it. Here I'm showing, usually it's showing L times L plus 1. Here I'm just showing you CL directly because it's a little bit more convenient for the instrumental noise. So here the E modes that we were looking at before, I'm not showing the temperature in this case just because it's very bright up here, and both really measure that at high sensitivity. But for the E modes, which we're mostly interested in, you see here the signal, and then here the gray is the noise curve associated with the large aperture telescope, and you see that you really have very good noise properties. Out to L of 3000, you will be able to measure the E modes, but you don't really have good sensitivity on the degree scales where you're hoping to detect the gravitational wave signal. And so for that, they're the small aperture telescopes that have very nice noise properties on large scales. And then because the resolution is limited, eventually their noise blows up and you can't hope to detect the small scale polarization information with them. It's a little bit more complicated than that because they are the lensing B modes that are here, and they are larger than the gravitational, presumably larger than the gravitational wave B modes that we're looking for. And you can't disentangle that with a small aperture telescope by itself. So what is being done is that to have a hybrid where you have both a large aperture telescope that maps out the small scale polarization, which can then be used to remove the lensing signal, which then allows to use the maps from the small aperture telescopes together with the lensing templates that you obtain from this to detect the primordial gravitational waves. So this is the motivation why the experiments going forward have this hybrid design that consists of a large aperture telescope and a small aperture telescope. And you see that in all the experiments going forward. So this will be the case for the South Pole Observatory, which is a union of the South Pole Telescope and the BICEP Keck series of experiments. And this will also be the case for the Simons Observatory. Both of those are supposed to start taking data soon. Everything is a little bit delayed because of COVID, but actually a lot of work has still been going on. So people were building the telescope here in San Diego. In fact, in the high bay, they were still allowed to do some of these things. And so this will somewhat be somewhat delayed, but not too much, and eventually take data from Chile. And here's the experiment that I was asked to talk about. This is CMBS4. This will essentially be the entire US CMB community coming together. Simons Observatory, South Pole Observatory, and observing the CMB from two sites. There's the South Pole site that will be dedicated to the observations of the primordial gravitational waves. And then there will be observations from the Chile site. The difference is, of course, that for the South Pole, you cannot continuously look at one small patch and you can make very deep maps, which is good for the primordial gravitational wave search. If you want to detect the small scale polarization, you really want to observe as much of the sky as possible. And so here you're using the sky rotation in Chile, which allows you to observe a large fraction of the sky. Before I say more about the sensitivity of S4, I want to briefly motivate why the sensitivity for S4 is what it is. And so I think everyone knows that the signal we're looking for is the primordial gravitational waves generated by inflation. I think everyone is also familiar with the idea of inflation as a period of nearly exponential accelerated expansion of the early universe. The simplest models you can write down that lead to a sufficiently long phase of acceleration that actually ends is just gravity coupled to a scalar field with some potential. The potential has to have certain properties, so it has to be shallow enough, at least somewhere, which are these slow roll conditions. If that's the case, then the scalar field then is nearly homogeneous and in a place in field space, so the potential energy dominates and these conditions hold. Then this leads to a period of exponential expansion. And this predicts that the primordial fluctuations are well approximated by a power law. The exponent is usually called ns-1, just for historic reasons. There's the -1, which means that ns equals 1 is an exactly scale invariant spectrum. It's expected to be dominated by density fluctuations, but one expects to also have a subdominant contribution from gravitational waves. The difference in amplitudes is set by 16 times the slow roll parameter epsilon that I had on the previous slide. The fluctuations are expected to be close to Gaussian. They're expected to be adiabatic, and one expects a universe that is nearly flat. And these are all consistent with observations, which is why people are interested in the model and are taking the prediction seriously. And so we may ask, in such a model, what amount of gravitational waves do we expect? So here, this is not a completely airtight argument. It's more a heuristic argument that doesn't depend on any of the microscopic details of the model. So here, let's assume we know the measurement. I didn't show the number. I'm assuming many people have seen it. So the ns-1 is not exactly 0. Ns is close to 1, but it's slightly lower. Let's call it 0.96 for now. And so that departure from the exact scale invariance, this small departure, is consistent with the idea that it goes like some order one number divided by the only large number that there is in the inflation models, which is the number of inflation, the number of e-folds counted from the end of inflation at which the scales of interest exit the horizon. So this is typically around 60. And so this gives you the observed scale dependence. And then if you if you assume that the slow roll parameter is small, then one can derive an equation of motion for the slow roll parameter in terms of this ns-1. If we take this and plug it in, you can solve for the slow roll parameter and you get this expression with this a first order differential equation. So there's one integration constant, which is this n equality. And there are typically you expect this to be order 1 unless there's some large or small numbers or hierarchies in your problem. And so if you have if you're away from the special point, if you're away from the special point where the two terms compete, one of the two will dominate. So either the one dominates or this one dominates. So there's really only two types of behavior that you would expect. One is epsilon just going like 1 over n. You can then reconstruct what the potential is, and it turns out this corresponds to the monomial potentials. Similarly, sorry,
5 minutes.
Okay. And then the second option is that you have the plateau models, where it goes like 1 over n to the p, where you can reconstruct that you have the hilltop or plateau models. For the monomial models, we know that they're essentially already excluded by current data. So there could still be that there's some fluctuation one way or the other, but it looks like the monomial models are essentially included. So the main focus going forward is on the plateau and hilltop models. They're a little bit more complicated to discuss, but not much more, just because they have one characteristic scale that enters of the potential. So there's the scale over which the potential drops from being going from the plateau to the minimum. There's some scale associated with that. It's not really the same as the field range that is often discussed. This is really just a property of the potential. And you can evaluate the integration constant in terms of this scale. And if the scale is of order in Planck, then this is of order 1, as you might have expected. And m of order in Planck is interesting because this happens in many models, not by accident, but because they really have a common origin. This happens, for example, in the Starobinsky model. I can say more exactly why that is, but maybe let me move on for now. There's Higgs inflation, fiber inflation, Poincare disks. They all don't accidentally have the characteristic scale of order in Planck, but just really because they have the same origin. And this is the class that the CMB experiments going forward will be targeting. So these are all within reach of CMBS4. If these are the models that are realized, then this is something that CMBS4 would detect. So this is the science goal, is a robust detection of primordial gravitational waves, or an upper limit of 10 to the minus 3 at 95% confidence level, just because it rules this out. The main challenges are weak gravitational lensing that I already mentioned, and galactic foregrounds. I won't say much about them. I'm happy to discuss them in a lot more detail. Here, I wanted to mostly focus on the science, but here the issue with the foregrounds is just that even in the cleanest parts of the sky, if you look at the CMB signals that you might expect, and you look at the foregrounds from synchrotron or thermal dusts, polarized emission from synchrotron and thermal dust, then you find that they always dominate. So you definitely need multi-frequency degree scale polarization measurements to remove the foregrounds. This is somewhat limited what you can do on the ground because of the atmosphere. So they're what are known as atmospheric windows. And this is basically what sets the frequency bands that we're using for CMBS4. So you can observe at 20, 30, 40, and 85, 95, 145, 155, 220, 270. I can say more why these are split like this if there's any interest. But in any case, this is what the current bands look like. And really also this limitation makes it natural to look for the cleanest regions rather than trying to go too wide. For the lensing, this provides an effective, essentially 5 microkelvin K arc minute floor, comparable, has the same L dependence as white noise would. And so going beyond this floor really requires high resolution polarization data, which is why the experiments have this hybrid design that I mentioned. I don't have time to describe these in detail, but we've spent a lot of time on simulations. And so everything looks like it works as advertised. So based on the simulations, it seems one can control the lensing and one can control the foregrounds, but this is still continuously being improved, but everything so far looks like it works. And putting everything together, this is the NSR plots that you might expect from S4 by the end of its observing time. Here the current constraints, and then this is what a detection would look like if there's a signal of 3 times 10 to the minus 3. And this is what the expected upper limits would look like. Again, these are the current constraints. These are the constraints that you might expect from South Pole Observatory or Simons Observatory. And you see that CMBS4 is yet another significant step up in sensitivity and really excludes the models with a characteristic that naturally predict the scalar spectral index with a characteristic scale that's larger than the Planck scale. And so this is the kind of measurements that you can expect from CMBS4. Just because I'm a member of these as well, I wanted to briefly also advertise Lightbird, which is a satellite mission that was selected by JAXA in 2019, is scheduled to launch in 2028. Has a different philosophy. I can say more about it if there's any interest. But similar raw sensitivities, so targeting similar sensitivities for the tensor to scalar ratio. We always also worked on a probe mission study that was called PICO. This would be significantly more sensitive, but it's also further down the road. And so there's also not tied to the gravitational waves, but an interesting direction of really measuring the spectrum of the CMB again, which hasn't been done since FIRAS. So with that, let me conclude, and let me just say that the CMB has really provided us with invaluable information about the early universe for a long time now. And it'll do that at least for another decade or so. So there will still be interesting measurements and science results coming from the CMB. It's exquisitely sensitive to primordial gravitational waves that are present at recombination. And they are a pristine relic from the early universe. And I think either detection, so what's interesting, I think, about this new set of experiments is that either detection or an upper limit will actually be very valuable. To achieve these goals really takes unprecedented levels of control over delensing, foregrounds, and takes a lot of work. So far, it looks like everything is working, and we'll keep working on it, and then hopefully we'll have some nice data and results in 15 years. So with that, let me just say thanks again for inviting and for organizing.
Great, thank you very much. Are there any questions? Just go ahead and raise your hands. Yeah, Mark Heinmarsh.
Hi, thanks for a nice talk. It's very exciting future in CMB. So I'd just like to, there's been quite a lot of talk at this conference about cosmic strings, and as I'm sure you know, they also produce P modes. So for example, the abelian Higgs strings would produce spectrum peaking at around L of 600 up to something like 10 to the minus 2 microkelvin squared. So I was just wondering how CMBS4 is for that kind of a spectrum.
Yeah, I mean, for that, I guess I can show you the noise curves again. But CMBS4 is I think, still provides interesting constraints, but I think other probes by now are starting to be more sensitive to the gravitational waves from the cosmic string network. So CMB provides constraints, but it's not necessarily the most competitive constraint anymore for the cosmic strings. If there's a signal, of course, and it's large enough, then I can try to go back, although that's probably not the most efficient way of going about it. So it's not designed exactly for that range, but you see that the sensitivity is still quite good if you look at the sensitivity curve. So it's not yet degraded too much. So there is good sensitivity in that range still.
Okay.
And it's also the large aperture telescopes at that point are starting to be good. So I think you will have good sensitivity for this also. Okay,
that's CL and not LL plus 1 CL.
Yeah.
Over 2 pi or anything. Okay, yeah. Right. Yeah. Okay, thanks.
Are there any other questions? If not, I guess we should move to our next speaker. So thank you again for that talk. Right, our next speaker is Oliver Buchmuller, who'll be telling us about AON and EDGE. So if you can go and share your slides. Yeah. Can't hear you. I think you're still muted.
Oh, sorry. Is that better now?
There you go. Yeah, I can hear you now. If you want to put your slides to full screen, perhaps.
I will. I just wanted to say that I have to stop my video because I cannot do both. My bandwidth is not good enough. Just so that people know.
Great.
All right, this should be now full screen. First of all, thank you very much for the invitation. Yeah, thank you for the invitation. So this talk today, which is the last one before the panel discussion, is really about the use of quantum technology to explore fundamental physics aspects, either terrestrially or in space, concerning dark matter and gravitational wave physics. So the preface, I mean, these are two quite complex projects, which I would like to describe in my presentation, namely AON and EDGE. So I gave a short preface and an outline because in 20 minutes, you don't really have the time to give too much of the details. Starting with AON, this is at the moment still a rather UK-centric project, which essentially has been funded very recently with about 10 million to start building prototype versions of quantum detectors based on strontium atom interferometry to demonstrate the capability of using this technology in order to start exploring ultralight dark matter, but also then eventually, hopefully, gravitational waves. It has a significant involvement of high-profile UK institutions, and at the moment we are building up with this 10 million the corresponding technology laboratories across the country in the UK. Based on that technology, we also have been proposing, and this is now a much more international project, a space mission proposal, which we have baptized EDGE in the Voyage 2015 white paper call. And that is now really bringing together a much larger community, which is not just the UK, but really reaching out to international collaborators. There's more than 200 scientists which have been signing up on the idea of building a mission proposal that utilizes quantum technology in order to essentially eventually then cover the mid-frequency gravitational wave, but also ultralight dark matter. So it really brings together many of the terrestrial projects where ION is one of them, but then there's also MAGIS, there's MEGA, and there's SIGA in China. So there's many terrestrial projects which are coming together and working, if you like, as pathfinder towards this space-based mission. I will say a bit more about these two projects as we go along, in particular focusing on their physics potential. Starting now with ION, ION really had the idea of a long-term vision, which consists really out of 4 stages. So the ION project I was just introducing to you really refers to stage 1, where in stage 1, we are really trying to establish the prerequisite for the technology using strontium-based atom interferometry as a demonstrator and a prototype in form of a 10-meter detector, which we would like to build in Oxford to demonstrate that this technology is possible, and then immediately scale it to a 100-meter detector, which at the moment we are looking for sites. This could either be in the UK, but possibly it could also be at CERN in one of the LHC shafts. So that would then be stage 2, scaling the technology to a 100-meter detector. And this is the current focus point which we are pursuing. As I mentioned already, that is now being funded at a level of £10 million, which is initial startup funding to essentially develop further the technology. Stage 3 and stage 4 are then really long-term visions of the program. Stage 3 is then the idea to use this 100-meter detector to scale it to a kilometer scale detector. This could again be, for example, in a mine in the UK, the Bolby mine, where we have shafts which are reaching down to 1.1 to 1.4 kilometers. But there's also other potential places around the globe which we could envisage to establish this detector. This would certainly be at the time scale of 2030 and beyond. And the ultimate stage, and this I have already introduced to you, is the idea of bringing this technology to space. And that would be, if you like, ION stage 4, or we have baptized it as it is now really an international program, EDGE. And here we have already started to build the prerequisites of an international collaboration. And we'll say a bit more about the context and the outcome of this Voyage 2015 call and how this could help to realize such a space mission proposal. So this brings me immediately to EDGE. So EDGE goes back to a workshop in 2019, which we have been organizing at CERN, in particular with a lot of help from John Ellis, who is also connected here today. So we're really trying to bring together different communities, namely the cold atom community, which is the stakeholder of the quantum technology we would like to exploit to do the fundamental science. But then we also brought together communities who are interested in the fundamental science as their primary research goal. This is particle physicists, but also people doing cosmology and gravitational waves, and a lot of theorists as well. So that was an interesting workshop which dates back to 2019. It was quite successful. It was still at the time when we had in-person workshops, so we had more than 130 participants coming to CERN and sharing their ideas between the different communities. And we were really reviewing the entire landscape of projects which could help and inform a space mission proposal, which is obviously something which is 15 to 20 years at least down the road. And out of this then came this paper, which is a full mission concept, if you like, a high-level mission concept. Obviously, several of the technical details have not been worked out, but it was quite successful and it was resonating with a rather big community. So we had eventually more than 130 authors from 70 institutions based in 23 different countries signing up, and then eventually also published this as a paper in EPJ Quantum Technology. This was inputted to the, at the time, open call of Voyage 2015 from ESA, which was essentially planning the landscape for the next big mission proposals ESA would like to roll out, starting basically from today onwards. So that's the very high level potential mission design. So it's really focused on 2 satellites which are being connected over a large distance. And here we were choosing the medium Earth orbit, which gives us around 10⁷ meter of distance between these 2 satellites. So these 2 satellites will be connected, and that's the idea, by a laser beam. And each of these satellites will then have 1 atom interferometer running a sequence so that we can perform a differential measurement as we would do in the terrestrial experiments on Earth, but now over a much larger distance, which obviously would enormously aid the sensitivity projection of that experiment. So that is, if you like, the mission profile outlined in a nutshell. So now I would like to come to something which is related to this, because this was something which was dating back 2 years ago. And today, finally, there's a little typo in there. This should be ESA Voyage 2050 recommendations, not 20,250. So these are the recommendations which just very recently came out. And they were very positive in the context of quantum technology and the idea of utilizing quantum technology for fundamental science in space. And I've copied here an initiative which we're currently running in the different communities interested in the exploitation of quantum technology for fundamental science, namely to start a community building aspect. And I don't read all of that out in detail. It's just for people who have an interest into this. So we have been putting together a letter which we would like to send to ESA to essentially demonstrate that there is across Europe a strong interest in the main stakeholders of the quantum technology, but also on the fundamental science, who endorse the recommendations as they have come out to build up a quantum technology development program to make this important aspect of the technology ready for space. And we encourage people to read that letter and to eventually, if they agree with it, to co-sign it. So this is still something which is open as a community aspect to co-sign here, and you can just put your registration in here in case you have been interested and feel like this is something we would like to focus on. And we will follow up with another workshop somewhere in September this year. So that brings me then back to the general concept after this little advertisement introduction to ion and edge. So what is atom interferometry, and why is atom interferometry potentially interesting to do the fundamental science of gravitational waves or ultralight dark matter? And for that, as I don't have much time to really go into the details, just give you a short comparison with something which I think most people are basically familiar with, namely with a light interferometer. And we just compare here the basic concepts of a light interferometer with an atom interferometer. And here the main difference is that the active element in an atom interferometer are obviously the atoms instead of the laser light. And the laser light basically acts as mirrors in order to essentially separate the 2 atom clouds from each other and to converge them back together. But other than that, the concept by itself is very similar, but it has some advantages. Obviously, it's a long way to go to demonstrate the technology to that level, but it has some advantages, assuming we can really demonstrate that this technology works to the precision we would like to have. So this is a short introduction of how it works. There is more in the backup, if you like, and being interested in. Now let's come to the physics potential we could do with such an atom interferometer. The interesting thing is that if you build an atom interferometer, it will not only be sensitive to gravitational waves, but it will also be sensitive to what we refer to as ultralight scalar dark matter. And the idea here is that, for example, if you have in nature realized, if, obviously it's a big if, but it's one possible incarnations of dark matter cloud, an ultralight dark matter cloud, which penetrates the atoms in our atom interferometer, it will imprint a well-defined frequency which is characteristic for this dark matter, and this frequency then essentially can be measured in this atom interferometer sequence with actually quite impressive precision, if you then believe the technology is being able to live up to these expectations. And it will bring, as you can see here, for various different coupling scenarios, so coupling to electrons, coupling to photons, but even also Higgs portal-like couplings, significant improvements in terms of sensitivity to new parameter space, both for linear coupling scenarios as well as for quadratic coupling scenarios. This is an ideal way to search really for ultralight dark matter. In particular, if you could bring it up to space, you can really see that EDGE is really carving in a lot of parameter space here in this ultralight dark matter scenarios. So ION and EDGE are probing, and that is the idea, ultralight scalar dark matter. But there's another interesting aspect of this atom interferometry, which you cannot have with laser interferometry, is that you can alter the sequence in the way how you essentially operate these atom interferometers, and you, with these alterations, might be able then to also search for different incarnations of dark matter. So not only scalar dark matter, but also axions, which are pseudoscalar, or even vector dark matter, which all sit more or less in the same potential parameter space. And this is something we're currently investigating, of how to alter this atom interferometer sequences to also be sensitive to these different species of dark matter. And needless to say, a space-based version of ION, which, as I said, we baptized EDGE, would have really unprecedented discovery potential for these various different species of ultralight dark matter. Now let's come to another important aspect, and that has been the main driver of using and exploring the idea to use atom interferometry for fundamental physics, namely to go into the mid-frequency gravitational wave band and to see what we can do there. And if you really look into where we are today in terms of an experimental landscape, and here I'm showing you the characteristic strain as a function of the frequency, where you will see the sensitivity projections from various different future experiments. So that we have on the right side, in the high frequency range, we have LIGO, which potentially then could be pushed into Einstein telescope if then this would be realized in the same frequency band. And then obviously we will have LISA, which by now is an approved experiment, which has the potential to really go to very low frequencies. But then there's obviously a realization that there is something in the middle, which is experimentally today not very well covered. And this is what I refer to as the mid-frequency band, which could potentially be very important in order to really have the full coverage of the frequency spectrum, but also to observe, for example, intermediate black hole mergers, but also other aspects which are quite relevant. So that was one of the drivers to see what we could do with quantum technology in order to fill that gap. And if you look what an ion experiments could do, if we were to go to a kilometer stage, as I was projecting to you, which we hope is some possibility starting somewhere around 2030, then you can see that you really be able to start filling that gap. We're already with a terrestrial based experiment, but then needless to say, if you were be able to really then go up to space with an experiment like EDGE, then you would really start filling that gap even more comprehensively. It would even give you some redundancy and overlap with LISA, but obviously EDGE would take place at a different time scale. So there's not really a competition between LISA and EDGE. It's just more like a complementarity an EDGE mission proposal would have with respect to LISA to fully fill this intermediate frequency range. So moving on, another interesting aspect of this mid-frequency spectrum, which I just like to mention, is obviously the idea that in this mid-frequency, potential signals will last for several days, if not even weeks and months. So one possibility you have in the mid-frequency range is to really utilize the rotation of Earth in order to essentially pointing determination or sky position determination, and that has been worked out, as you can see here. And an interesting aspect is if you were to operate even two experiments on Earth, that would help you to even further improve that sensitivity by taking into account the additional rotation. And that is one of the goals we are aiming for on the terrestrial aspect. So ION is an experiment, as I mentioned to you, which is currently being spearheaded by the UK, but we have to hope that this becomes more European dominated. And we are already partnering with a similar experiment in the US, which is called MAGIS, pursuing a very similar goal. And what we would like to establish in the next couple of years on the prototype version is to set up a LIGO-Virgo style network already between these prototype detectors to demonstrate what one could do by utilizing atom interferometry and simultaneous operations between these experiments. Another interesting aspect, and I wish I would have more time to cover this here, is that it's not only astrophysics you could do with an experiment like ION or EDGE. Once you then have reached the sensitivity, there's also a lot of other fundamental physics of interest. And, you know, to someone like me who comes out of the particle physics camp, initially, for example, putting on constraints on the graviton mass is certainly something which is very interesting. And here, John Ellis and Willem Vascon, I think John for sure is connected to this meeting. And if there are questions, he can say more to this study. They have investigated the possibility of how far one could push the limit on the graviton mass as it is currently being quoted by LIGO and Virgo, as you can see there from the recent analysis, by basically looking at the mid-frequency range, in particular looking in ION and the EDGE experiments, by having these different ansatz here, first for the one of the mergers and then also for a larger parameter space. And I think what is really interesting here, and what I think is an interesting eye-opener as well, is that if you are able to cover the mid-frequency range and have sensitivities that, for example, EDGE or even an ion kilometer detector could reach, you really can improve very significantly on our current sensitivity towards fundamental quantities like the graviton mass. So this is, for me, quite important. There's a lot of interesting physics one could do once we are starting really to explore this mid-frequency range, and then therefore have full coverage of the entire frequency, including LISA and potential then Einstein telescope. There's a lot of other fundamental physics which we're currently exploring. One could do basically the measurements we are planning. And this is just a shopping list, if you like. I'm not going to go too much into the details, but this is something a bit more in details as we go along. So then this brings me also basically already to my summary. So there is a lot of potential and interest in various different communities to start exploring the potential quantum technology has for fundamental science. And here in particular, I'm talking about atom interferometry, which is based on the single photon transition of strontium. There's a lot of research and development and investments already being done in different countries like the UK, the US, but there's also many activities ongoing in Europe, for example, with MIGA in France, but also in China. And we are really starting to build up an interesting potential here. And obviously EDGE would then be the ultimate goal of a uniquely interdisciplinary mission, which then would harness this cold atom technology in order to start exploiting fundamental physics. So I think I'll leave it here. I only had 15 to 20 minutes anyway. Thank you. Can you still hear me?
Yeah, I still hear you.
We can't hear you for some reason.
Did I drop out? It's my internet, maybe.
No, I hear you. I don't know that.
I think we don't hear Michael.
Not Michael.
Yeah, we don't
Yes.
hear Michael, right?
Anyway, I think Michael would open. So if there are any questions, people, please shoot.
Yeah, sorry about that. I had some audio issues there for a moment. Sorry about that. Thank you for the talk. Yeah, are there any questions? Please go ahead.
Salvatore.
Yeah, thanks, Oliver. Thanks for the talk. I have a question about the massive graviton, just to be sure I understand. Because that's a pretty much a propagation violation of GR rather than a generation one, I think the constraints get better if the source distance increase. And can you, I don't think you mentioned or I missed the horizon on which you can see these objects that you will use for the test. Is that really compatible with the LISA and next generation ground that will see Z of 6 or larger?
I can try to give you an attempt of an answer, but I think John, who is one of the main authors of the paper, is connected. John, you want to take that?
Well, I think the simplest thing, Oliver, would be if you could show the overall sensitivity curve where you've got the signals as a function of redshift.
This one? Or the signals? This one here? Yeah.
No, the sensitivities of different detectors, including AON and EDGE.
No, I don't think I have this in my slide.
Oh, yeah, you showed it.
This one?
No, one of your other slides.
Oh, you mean like the characteristic strain? Sorry, yes.
Yeah, number 17. That's good. Yeah.
Mm-hmm.
Okay, so I think Salvatore, this may help answer your question. So you can see those lines correspond to different values of the redshift. And for example, with EDGE, you can see the merger of two black holes weighing thousands of solar masses out to a redshift of 16, which I think is, as far as one might reasonably expect to be able to see such things.
Okay, absolutely fantastic. Sorry, I had missed the redshift labels in here. Thank you very much.
Right, I should have pointed it out, but I was a bit conscious with time, so 20 minutes.
Are there any other questions? If not, let's thank our speaker again, and just a big thank you again to all the speakers from this session. So I'll hand it back to the organizers. Thank you, everyone.
Thank you. Okay, so we're almost on time, so we'll meet back for the discussion 10 past in 4 minutes.